gigabit switch or a 10 gig switch or a 40 gig switch, and you just want to make sure it has enough throughput. On the SD-WAN side, a lot of the challenges or a lot of the limitations are on the control plane. Has to do with, we'll see where this is coming from. Won't want to get too much ahead now. The first question here on the perimeter side is what are the typical limitations in software and hardware? The second one is how can you complement existing services with SD-WAN, especially in the hybrid cloud and hybrid WAN solution side? And in which way is it possible to improve a data center? So control plane limitations. A big major component of an SD-WAN solution is the controller. The controller is responsible for setting up tunnels, for maintaining them, for managing them, for tearing them down, and so on. The controller doesn't actually participate in the data plane, so it just steers all of the endpoints and the head end. But the controller still needs to maintain everything, so it's important that the controller can keep up with the scale of the network. And this is a very trivial but also still important diagram of the number of sites versus the number of tenants. For a controller, it doesn't usually make a lot of difference whether I have an additional tenant or an additional site. What's clear is the larger the number of sites is, the lower the maximum number of supported tenants will be, and vice versa. So all of these things have to be taken into account. And from the testing perspective, what we often see is data sheets, brochures, flyers, have all sorts of wonderful data, and typically each item is measured separately by vendors. So let's say they configure their solution to be optimized for the number of tunnels, and they say like, our controller supports 10,000 tunnels, check. And then they say the number of CPEs, our controller supports 20,000 CPEs, check. Our controller supports 5,000 tenants, check. But unfortunately, these are mutually exclusive. So, and that's often overlooked. So it's not that, all of these numbers can be scaled at the same time. There are some interdependencies, and it's important to take this into account. Usually, I think for today's deployments, it shouldn't be a major deal, but on the service provider side, if you want to grow your service largely, it's important to understand what are the limitations per controller and when is it the right time to introduce an additional set of resilient controllers to support network growth, service growth. So the last one here is routing information-based table size. So some tenants have pretty complex networks internally, and it's important to understand how the routing table will grow as well. So how can the service provider and its customers scale out? I said the number of sites can be increased, the number of customers, then the number of controllers needs to be increased. Multi-vendor support is maybe necessary if the service provider decides to go with one solution in one metropolitan area with another solution in another region. And the CPEs also need to look at their control plane limitations. A CPE typically is a piece of software or hardware that has limited compute power. Limited compute power means it's cheap, which is great because you don't really want to buy a 3,000 euros or dollars HP DL380 Gen 10 server as a CPE. That will have a lot of compute power, but it's way too expensive, takes too much power, too much space and everything. So it's limited. And it's important to understand what its limitations are. CPE vendors put a lot of effort in making sure that the limitations are well balanced, and I have lots of respect for them. Still, it's important to make sure that the given CPE matches your requirements, especially on the numeric, on the quantitative parameter size. So how many firewall policies can be supported? Many people will need only 10, 20 rules, but some enterprises have really complex access control lists, so a lot of firewall policies need to be supported. Some people have a lot of threat management rules, those might need to be supported. And then they take the performance away on the control plane side from supporting the maximum number of IPsec sessions or the number of routes that are supported and so on. So all of these things are connected, and if you look at the generic CPE software architecture that our team drew here, the data plane side here north of the dashed line, firewall forward information base, is pretty straightforward. It can be well understood, and it's either in hardware or even if it's in software on a virtualized CPE, it's supported by the standard Intel data plane development kit, maybe DPDK. It's pretty straightforward. But the control plane side has a lot of interdependencies and way more modules that need to scale at the same time. So their solution parameters interfere with each other, and they influence each other as well. So on the controller side, the interesting question is how to scale the number of controllers in a service provider network. One controller for sure is not enough. So obviously this is a rhetoric question on the slide. That will be a single point of failure. That's never good and highly risky. So now the question is, how many controllers should we have? Okay, let's have 2. But 2 are only good for backup normally. If you have 2 controllers, you always need to anticipate one controller will fail. So in the end, you only end up with one controller being the scale limit again. But now we're not talking about redundancy. In this section, we're talking about scaling the service numerically, quantitatively. So in order to increase the capacity of an SD-WAN solution on the control plane side, very probably there needs to be a cluster of controllers, more than 2. So if there are 3 or more controllers, that definitely improves the scalability of the control plane as well, and of course the resiliency, but then the whole solution becomes more complex. So it's important to take this into account for validation. If you want to deploy a cluster of controllers, test that cluster of controllers and see how it works if you plug out one and then the other and then the next one, and if the services actually are rebalanced if additional controllers come back online. So on the data plane, the limitations are straightforward, as I said. I think they're very well understood. Still, it's an interesting topic, especially because we need to emulate quality where there is no quality in the underlying network. So quality of service cannot be guaranteed on the internet, obviously. I mean, maybe some ISPs have higher and low priority, but I think generally, no, don't assume anything on the internet. So we could either say, the internet is as it is, it's low cost, so don't complain. Or we could improve things. And there are solutions like forward error correction, for example. Sending packets multiple times, sending them in a way that they're interleaved. And actually, it doesn't matter so much if one packet is lost. There are some solutions that actually correct the order of packets. In the internet, it can often happen, or sometimes, it can happen that packets take different routes towards the target. So it might be possible that even if you send packet 1 first and packet 2 second on the same link, they might arrive at the destination in the reverse order. In that case, any IP protocol, like TCP, for example, any transport protocol will throw away actually, they will throw away both packets and ask for retransmission because the order is incorrect and TCP can't handle that. But if the SD-WAN solution can fix it and can correct the order, wait a little bit, have a little receive buffer, be a little smart, then it might actually be much better performance, although the quality of the internet is still the same. The next limitation is the encryption algorithm. I already talked in the requirements section about different ways of encrypting. So the ciphers are really important, and they can be a real drag on the compute performance. But then, unfortunately, more modern ciphers are really critical in many scenarios. So you can't just use the cheapest and oldest ciphers just because they compute better. So the encryption algorithms create a lot of limitations on the data plane. It's important to test and validate the solutions with the right encryption algorithms. So we talked about encapsulation and maximum transmission unit, like packet size, fragmentation issues already. The encapsulation overhead is an interesting topic. Some additional features, of course, require additional encapsulation overhead, and it's a question of balancing those overheads with the requirements of the maximum transfer unit size that needs to be supported without fragmentation. So I talked about IPv6. So IPv6 is nice requirement on the functional side. It needs to be supported on the data plane with good performance as well. What we're often seeing is in firewalls, for example, still today, IPv4 is optimized. IPv4 is the bulk workload that everybody uses every day. But now IPv6 is rapidly increasing. Many services are only available or are better available on IPv6. And so there are many reasons for IPv6 ratio of traffic increasing. Now, in some implementations, IPv6 is still supported in a less optimized way, or only in a software way if there is hardware available that would optimize IPv4. So IPv6 support is not only a functional requirement, it's also a quantitative requirement. It's a requirement of checking if the throughput is the same if it just sent IPv6 packets compared to IPv4. It's a very old threat that we've seen all across the telco industry, but that's the case still. And finally, a very nasty one is multicast. Most people don't need it, but if you need it, you might be in really bad shape because multicast requires splitting, replicating packets at different points in the network. And especially, let's say, if there is your CEO talking to all of the supermarket branches at once, and you have the head end requested to replicate a multicast packet to 1,000 endpoints, I'm sure it's going to be a wonderful test scenario, and I'm not sure if anybody would survive that. So multicast support can be pretty interesting if it's needed. Fortunately, it's not needed in most cases. So then on the data plane limitations, especially if we're talking about virtualized CPEs, I think virtualized CPEs are the future. I mean, they are so much more easy to handle. But you still need some sort of hardware solutions in specific cases. So usually the business case doesn't work well if there are really high performance requirements. Let's say your head end has 10 gigabit, 40 gigabit connectivity. You have or it needs to support even 1 gigabit throughput with a very complex cipher. So the throughput limitations usually still sometimes in this industry lead to the requirement that we will have to have physical CPEs. There are also requirements in adverse environments, as I said, at hot temperatures or some specific things where maybe an x86 CPU will not survive easily. You know, x86 architectures can only get that so hot and they emit a lot of heat. So in many cases, physical CPUs are still required if the vCPE concept is not applicable due to some limitations. So going back to heavy reading once more, what are the implementation barriers that service providers and enterprises have seen in this heavy reading survey, actually sponsored by Huawei in the second quarter 2016. There were a total of 85 to 88 respondents, depending on which question. And the most important implementation barrier is actually integrating with the management system. So if you remember, management and provisioning was also the most important point that people looked after. So it's unfortunate that it's also seen as the most important barrier for implementation. Lack of integrated end-to-end solutions is the next one. You know, buying a pair of SD-WAN is nice, but it needs to be integrated. Okay, maturity is something that will solve itself over time, and I see that vendors are working very hard to improve the maturity. And then the next one is an interesting one, lack of education and skills. So actually, you know, educating the whole IT team in an enterprise, or even the support team for VPN, transport VPNs on the service provider side is an interesting challenge as well. So without going into more details here, I think we'll just focus on the most important one here, integration with existing OSS, BSS, and generally integration. How can the services be integrated, and how does this actually work on the performance side again? So the hybrid WAN use case has been used by large enterprises for many years. SD-WAN is a new concept, but it's not a totally new idea. everybody that had mission critical services always had multiple connections to a destination. And these were usually dual MPLS networks in some very large networks, or they were backup networks with leased lines or something like that. So it's actually quite interesting to use SD-WAN in specific situations. So I'm not sure if any of you has connectivity to Africa, but Africa is known to be one of the most expensive areas for transport networks still. So if you want to have a leased line and MPLS service to somewhere in Africa, it's usually the most important, most expensive business, part of the business. So, or sometimes it's very hard to provision highly reliable services in some countries. So it's actually good, it would be good if SD-WAN can be used to complement existing hybrid WAN use case scenarios and not just, you know, be the next generation and start from a greenfield. So that's one case where the solution parameter is quite interesting to understand. How can an SD-WAN solution be integrated with a service? How can it be managed jointly? Should the management be from the SD-WAN side or should it be from the legacy side? And how can this whole service then be maintained as an integrated part? The other point is the hybrid cloud. And one point, as I said before, is the connectivity of SD-WAN to public clouds. I think that's a pretty straightforward thing. People have thought about this already. That's a growing business. But for a hybrid cloud, for an enterprise that has internal clouds, for example, or that uses Amazon VPC's virtual private clouds or other cloud operators' virtual private clouds, that's actually an interesting point because it creates multiple hubs. It creates multiple endpoints that have special roles and are not CPEs. So these VPCs, virtual private clouds, would need to be connected dynamically to any site, which increases the number of tunnels again. So we're not in a hub and spoke scenario anymore. We're in a hub and spoke scenario. And obviously, going back to that orchestration challenge, it's important to integrate with the existing orchestrator for the private cloud. So the cloud operators say like, you know what, guys, we have a working service. It's really big. It's out there for a long time. We have well-defined APIs. So you are welcome to integrate with ourselves. We are not going to integrate with any transport solution out there. So the transport solution, the SD-WAN, needs to integrate with the existing orchestrator for the private cloud, not the other way around. So finally, which SD-WAN solutions can actually improve a data center? Let's go away from this focus on the CPEs for a bit. So what if we would just say data center interconnect is a challenge? And it always is. I've seen people that have actually started running dark fiber to interconnect their data centers. They started building redundant data centers within a certain reach and at certain geographic locations so they could be sure they would have good data center interconnection. If you can't do that, if you don't have this ability, you need to connect globally dispersed data centers without having huge budget to run a 10 gigabit dark fiber, then actually SD-WAN might be a good solution even if there is no single CPE site involved. So that requires, again, all of these features that I talked about in hybrid cloud, in virtual private cloud connectivity, because a data center is like a virtual private cloud. And SD-WAN can actually improve a lot of problems that have been seen before. I remember we had a data center test for a tier 1 in Northwestern Europe. And everything went well until the point we pulled the plug between the two redundant data centers. And actually, the solution never came up again. And the vendors looked at each other and said like, oh, bad luck, some routing problems. So disaster recovery and connectivity of redundant data centers can actually be improved by SD-WAN because it's more flexible, it's more agile. It actually has a number of features to improve the connectivity and the security and the resiliency. So what are the challenges? We have a lot of vendors offering solutions. Our team here called it promises. And what about the reality? What is the customer demand? What are the vendor solutions? How do we deal with high availability, scalability in fact? And how do things actually work with internet using solutions over the internet? Now, we all know that enterprises often, at least in some sectors and service providers even more, issue RFPs that are listing more features and more scale than they actually need. So they just say like, okay, we put this out there, we just put everything on the table, and you should be able to do everything. It's like if I go to an Italian restaurant and require, you should be able to do a perfect carpaccio and a perfect lobster and a perfect steak and a perfect dessert, and I will definitely not eat all of it, but I just want to be sure it's the best restaurant I go to. But so the problem is nobody can meet these requirements, or very few restaurants would be able to meet these requirements. So in fact, and they would be probably very expensive. So it's important to understand what do people actually need, but what they actually need should be existing. So let's see what do enterprises actually need today. So currently, SD-WAN is deployed by large enterprise customers. Large enterprise customers have certain needs. They need a large number of CPE sites, as I said. They need pretty complex routing topologies and so on. Smaller and medium-sized enterprises are only going to come. Their demand is going to grow slowly. I don't have the reference here, but I think we'll probably hear, hopefully, from a couple of analysts here this week about small and medium-sized enterprise business. Usually it has been inaccessible for service providers. I read something like in Germany, 95% of the small and medium-sized enterprises have no transport network other than the internet connectivity. So actually tapping into that uncharted territory would be really cool. That demand will certainly grow. But those small and medium-sized enterprises have totally different requirements. They don't spend so much money. They can't afford, managing a complex environment. They have only a few endpoints, and they don't need that much high availability. So their demand is very different. But there are a ton of small and medium-sized enterprises. So if a solution has been focused on the first customer group, it's optimized for one way, and if it focuses on the second customer group, suddenly you need to have 10,000 tenant support. And we've seen this from, I'm not sure if it was public, but we've seen this from one tier one who said like they have 20,000 managed virtual CPEs in their vCPE service today suddenly. So it's a huge number, and it's a number that quickly grows from beyond a specialized service to something that really needs to be ready for the mass market. So SD-WAN hasn't reached its peak demand. Like any technology, it will eventually reach its peak demand. And in the way how it grows explosively in the last, I think, 18 months or so, I would say we're soon going to hit what Gartner calls the trough of disillusionment. We will soon see like SD-WAN does not solve all of the problems out there. It's a cool technology. It works really great, but it doesn't solve everything. And then the demand will grow again. But at some point, of course, the accessible market will have been covered, and the service providers may want to consider deploying services in advance of that peak. So being fast is actually quite important, especially for those customers that say, oh, we can save money. Let's deploy something fast. And then they probably will stick with the service providers they have commissioned in the first place. So what are the challenges here on the vendor solutions? I think we talked about this, so this is just a quick summary. Does the vendor solution meet the service requirements? Do they actually have a CPE that's ready? Do they integrate? Do they support the topologies that I need? Do they actually support distributed intrusion prevention, next-gen firewall, and WAN optimization, which is, that's an area where there's a lot of differentiation in the market. And do they provide high availability solutions when needed? Now, the scalability of controllers software under real-world conditions is quite interesting and important. So we have the different CPEs that run the data plane, and we have the controller that runs the control plane. They're connected with each other, and it's important not only to stress the data planes, important to stress the control channels by a provisioning activity. It's important to stress the controller's resources by scaling the controller. So there are multiple fronts, and it's usually important what we see to stress a controller not only to the max. Of course, I can break any software at some point. It's important to stress it realistically. Where do you want to be in 5 years? Let's say, how long do you want to run the solution? Let's say 5 years. How large will it scale in 5 years? What will be the target scale? And that's the target that I think is reasonable. Anything beyond that, like make and break destructive testing, is only important for vendors who really want to see, like, how does the solution behave if you exceed that scale. So how many controllers are needed? Distributed fault tolerance, I quickly talked about this before. It gets interesting if we look at some more detail of the distributed fault tolerance. So wait a second. Okay, right. So no, this actually, this diagram talks about the fault tolerance, the high availability at the CPE side, at the edge side. So if there are multiple CPEs, they need to synchronize with each other. And that synchronization, session synchronization with via RP, for example, and the routing synchronization with BGP or any other protocol requires the sessions to be, requires some time. So this, again, introduces operational parameters, operational consequences, like the failover might take some time, tunnels might need to be reestablished, it might actually take some time to detect a failure. The first part in failing over is always detecting something is wrong, and only the second part is actually failing over. And in many cases, the detection takes much longer time than the actual action. It's a little bit like if I'm driving a car and there's something happening in front of me, sometimes it takes longer to detect, I need to operate the brake than actually to get the car to stop. So a next challenge is the IPsec scaling issue. I talked about this a couple of times. So encryption requires more resources, needs to be taken into consideration. And IPsec becomes really bad only if there are spoke-to-spoke and full mesh connectivity requirements. If there is a CPE that has only 2 tunnels to 2 hubs, that's actually fine. It should work fine, right? But if suddenly I have to support many tunnels on the CPE, that might be an interesting problem. The other problem that can always happen in the internet is asymmetric routing. It's probably quite likely that there will be asymmetric routing somewhere in the network and internet. And it can also happen if you have redundant CPEs that not both of them switch over at the same time, so that packets are sent out on one CPE and they're coming back in on another CPE. That could also happen, and asymmetric routing should be validated, and if it's needed as well. One big problem with asymmetric routing is WAN optimization. So WAN optimization assumes that I can reduce the packet sizes, I can squeeze things because I have a bidirectional view of a connection. Let's say, for example, I'm not sending acknowledgement packets anymore. I'm not sending the full IP headers anymore. That only works if one optimization point has a control over both directions. In case there is asymmetric routing and traffic is going out on one CPE and coming back on the other, WAN optimization is not usually going to work anymore. So then the vendors need to really be very advanced in optimizing, or they need to avoid asymmetric routing. So asymmetric WAN optimization is actually quite a disruptive requirement if you have that. So internet, is it the Wild West? Okay, or wild whatever direction. Internet has no guaranteed QoS, we all know that. It's unpredictable, especially over long distance, but it actually gets worse. We had a customer recently from the automotive sector who said, like, well, we have factories all over the world. We have factories in Mexico, we have factories in China, we have factories wherever, you know, we build cars. And like I said, it's actually working great with SD-WAN in those Western countries, especially the US, you know, where there is no filtering, there is no special treatment of packets and so on. But it doesn't actually work well in China. In China, it works only on Mondays and Thursdays, and on Tuesdays and Wednesdays it doesn't because they do something with their big firewall. And some countries are blocking VPN usage completely, so anything that's encrypted will not be forwarded, like Iran, for example. Okay, not many cars are built in Iran, I guess, but there are some countries that actually block VPN usage completely. And some actually only block strong payload encryption. So you have to use a reduced, weaker encryption so that they're able to break this with their governments. So that's a problem. It cannot be assumed that SD-WAN services over the internet will work to any geographic locations. Maybe it's a minority problem, not sure. And the other point is that strategic partners are important, and I'll show you on the next slide why, or on the next two slides, or where was this? So it's important to have an SD-WAN solution that actually works together with an internet service provider or a cloud provider, a CDN, because then you can rest assured that the route over the internet will always point to the correct destination. What can happen is that BGP can be hijacked or can be unstable. For example, there is, I'm not sure if this is true. So for example, there was some problem in Japan recently where half of the network of the internet in Japan was down because Google decided to issue, I think, a default route, or at least a route for many destinations. And so a lot of traffic was forwarded towards Google networks instead of towards the right destination. And of course, Google didn't forward it further on, so it was basically discarded. And until, this can happen in BGP, so until a BGP infrastructure, the routing table was fixed, internet traffic just didn't work. And if your SD-WAN solution depends on the internet, then it will suffer. So BGP hijacking is important, and if you actually partner with an ISP or if you order a service through an ISP, then usually their internal BGP table will be more stable than the global one. So high-speed broadband is another issue, and unfortunately my home country Germany is one of the countries where this is an issue. We have something called a digital agenda, but we don't have a real good high-speed service. And so we are here on number 25. Around 33% of all locations in Germany have more than 15 megabit throughput on a consumer broadband network. Now you could say, like, okay, I can always throw a fiber to any place, but that's exactly the point, right, about SD-WAN, not to spend too much money. Because if you throw a fiber somewhere, then you can probably also afford a leased line and MPLS VPN service. So if you want to use a consumer-grade broadband access, then you cannot take for granted that you'll get a lot of bandwidth in Europe. So Switzerland is best, Norway is second, Sweden is third, and so on. And in some countries, it might not be easy to get to the multi-gigabit speeds that were mentioned in the heavy reading survey on one of my first slides this morning. So far about challenges, how to avoid these pitfalls. Of course, I really truly believe it's possible to create and deploy successful SD-WAN services today. Still takes a little bit of bleeding edge, of sweat and tears, but it should be possible. How to avoid these pitfalls. I said already, define your requirements. Start from the requirements. Don't start from what a solution provider can offer to you. Don't start like from a data sheet and so like, check, 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 I need this and that. Start from your own requirements. Start from your current service offering. Understand and evaluate what you really want to offer. If a user portal is needed, if so, with which features, and so on. what market position you want to have in the SD-WAN with your SD-WAN service. For many service providers, and I personally haven't understood that yet, and I'm going to listen carefully to what people say this week, is in how far does a service provider actually complement their existing service offering, in how far they understand existing service offering is too expensive, so they need to, they'll reduce market share here, they'll increase market share there. So that's an important question. Then, of course, what's the network size and topology? And especially in Europe, there are so many countries with different topologies. Here in France, many things are centered around Paris. In Germany, we have all of these regions that are equally important. Switzerland, I think, has 2 or 3 centers, and so on. So the network size and topology can be vastly different and can result in different requirements for the network. And of course, what underlay transport technologies are you using? Some service providers have a really good grip on their internet service offerings. So they can use it pretty well, and they might have internal SLAs available. Other service providers have focused much more on their traditional transport VPNs, and they might need to use MPLS or another technology as the underlay transport. So, how can you avoid this big management challenge? Management sits there like the big thing in the sky where it's like, oh my God, I would need 100 developers that can do Python coding and no web programming, and I can create a user portal with them. If it's possible to integrate with existing provisioning tools, it's way easier, of course. Use available APIs, use things that are already there. I think what I've learned from the open source movement that's so important in our industry right now is that very few people actually start creating something from scratch. People take things from here, from there, they integrate. So yes, you need to integrate, and yes, you need to have people that understand how to program a little bit, but it's no longer like you commission a big programming project to one of those big programming companies in Eastern Europe or India or wherever. Basically, a lot of building blocks exist. It's just important to combine them smartly. Enhancing the user experience, I think that's really the key point. Users love those portals. I think, if you just look at AWS and focus on what's possible there, that's already a great way to get some guidance. And finally, train your network team. Training and education is really crucial, as one of the results from the heavy reading survey also said. Training should not be underestimated. So, validate the solution, test the vendor in proof of concept tests, select them based on the test results. Don't buy at this point without validating what you're buying before you sign the contract. Identify the trade-offs. There will be trade-offs. And in many cases, when we test solutions, we find those trade-offs. And the vendors are often pretty scared. They say, like, I don't want my customers to find those trade-offs. They should just be happy. And in the end, it often turns out the customers are more happy if they understand the limitations and the trade-offs than if they're just thinking everything is white and shiny and everything will just work as great, because it won't. At some point, everybody's hitting the limitations. It's good to know those limitations in advance and to accept them. I cannot have scalability and resiliency and security to the max at the same time. There are some limitations, or it's becoming more expensive. And finally, perform interoperability testing with your current network. If you need to integrate in a brownfield environment, it's crucial to test if that integration will actually work. Some ideas on how to avoid interoperability issues. I think that's pretty much straightforward, and that's what we typically use as guidance for our tests. Now, which APIs actually exist? I picked the MEF reference architecture here, the Lifecycle Service Orchestration, LSO, that the MEF has worked on for quite a while. There are other activities in the industry as well on this northbound layer. So basically, the interesting question is, okay, we've sorted out all the stuff, in the basement. The whole thing works now. And now, how do I actually create a service from this? I need a service model. And the service model is what a lot of the industry activities, standardization activities center around right now. There is work in the Broadband Forum on managed objects environment. There is work in the IETF on service models for layer 2 and layer 3 services. There are many activities on the transport network side around netconf and Yang, for example, OpenConfig. And so the further northbound you get, the more advanced and the more complex the services become. So that's why I picked the MEF reference architecture here. So they actually aim to standardize SD-WAN architecture with the lifecycle orchestration model that has been available for roughly a little bit more than a year now, and a white paper that has just been released. And I've seen Daniel from the MEF here, so I'm sure he'll have a more educated talk about this later. So just 2 slides on this. Basically, the idea of this reference architecture is to define APIs for the essential functions. And I admit I haven't been to MEF meetings for a while, but when I still went, and when the service provider started with this initiative, this was really weird stuff. I mean, we were talking about protocols, and they talked about how to order a service. And I was like, yeah, isn't this something you can sort out internally? Actually, no. Ordering is the first part of the provisioning. So it's important to understand how to order a service, especially if there are multiple domains involved, if there's an enterprise and an operator, or if there are multiple providers and ordering needs to be sorted out across provider spaces. Then the configuration, that's pretty obvious. Configuration needs to be standardized. It needs to have an API that everybody can understand and follow. Because in the old times in the MEF and carrier Ethernet, we said, like, you know what, in the end, carrier Ethernet is very straightforward. It's just Ethernet with a couple of parameters. But the service providers never agreed on how to order it. They faxed around, some weird forms that everybody had their own forms. Everybody had their own ways to describe things. So it's important to standardize on these configuration options. And then, of course, billing shouldn't be underestimated, and there's another aspect that's important. So northbound and southbound APIs should be standardized for the service provider to enterprise interface, and east to westbound APIs for the inter-provider communication. So the MEF has defined some APIs here which have very memorable names, and I'm sure there's going to be more information from the MEF later this week. So there is a white paper which might help to understand this environment, especially the terminology. And that's actually, we're working with a new IP agency on terminology and taxonomy for telco cloud services, for NFV services as well. So I can only agree that terminology standardization is very important. And it explains how SD-WAN fits into their lifecycle service orchestration architecture, which has not been focused on SD-WAN from day one because they have worked on this for a longer time. So I'd be happy to start testing these interfaces. I haven't seen them deployed yet, but I'm sure they will be coming. And once they're available from EANTC's perspective, we'll certainly start testing Cantata, Allegro, and other APIs that the MEF has defined. And I hope it'll improve the interoperability. So what would be a typical test bundle? I think I can go through this pretty quickly and then go to my final part regarding this actual test experiences. We have a standard test methodology, like a building blocks set of test plan options that we usually pull from for SD-WAN testing. And they, again, center around these 8 areas that I mentioned in the requirements on the very first slide. So not much surprise here anymore if you followed the tutorial so far, so I don't want to bore you with going through this again. You see the scalability requirements, you see the multi-tenancy requirements, and we've created test cases all around this for each individual scenario. User portal management requirements. I think these slides are going to be available for delegates, in case you wonder. Endpoint configuration, what are the different configuration options for router, CPE, firewall functions, and security. And I think one point that I haven't mentioned yet which I hope to test with the vendor pretty soon, is also the security options. As long as the SD-WAN CPE is only, a handover point, a peering point between the local area network and a tunnel to a hub, yes, it's important that it cannot be attacked. Yes, it is connected to the internet on the transport level, but it is not so much of a threat. But if the SD-WAN CPE is actually breaking out traffic to the internet, which does make sense in most cases, then it needs to have a really advanced firewall. So the local breakout is important to reduce the amount of traffic that goes to a centralized hub. It doesn't make sense at all if an enterprise user wants to stream YouTube videos and that goes from one country to another country. Doesn't make sense. So it should be broken out immediately to local internet access if you're using internet anyway. Yeah, so those are some security and resiliency things that we test, different ways of failures. And actually in the virtualized space, it's quite interesting. There are many more things that can fail individually in a virtualized environment. In a physical environment, you pretty much look at boxes. The boxes are black boxes, more or less. So either they work or they don't. That's usually the assumption. Either a link works or it doesn't. So you pull the plug on a node, you pull the plug on a link, and those are basically the failure scenarios. However, in a virtualized environment, it can happen that maybe one virtualized router or one virtualized firewall doesn't work anymore, or one socket doesn't work anymore. I don't know, many things can happen. So basically the hardware becomes a white box. You need to open it, look under the hood, and create all of the different failure scenarios. And if your virtual firewall is stuck in a software loop and it doesn't work anymore, but the rest of the software infrastructure continues to working, then still the solution needs to fail over because it needs to notice it doesn't do its job anymore. So that's an important aspect of resiliency in a virtualized environment. So performance monitoring. In the performance monitoring space, I explained what we look for, latency and loss and other things. And this becomes quite interesting when one scales services. And actually, our home ISP already told me, yeah, they have a fiber to us. We only get a gigabit of throughput right now, but they could easily increase this, or we only get, I think, 500 megabit, and they can increase this to a gigabit without any hardware exchange, and it's just a little scaling and capacity management. So that scaling and capacity management is quite interesting to test as well, especially if you're trying to save budget on connectivity and not use all of the physical throughput available. So performance monitoring, it's quite interesting that it's not always accurate. So performance monitoring, especially if you take any decisions of failover or decisions of billing based on performance monitoring, we need to make sure that it's actually counting correctly. So if there are duplicate packets, if there are packets that have not made it to the destination, if the latency is measured, it's important to make sure that the measurements are correct. And latency is an interesting beast because clocks can run out of sync, and one-way latency is even more difficult in that regard. So accuracy of performance monitoring is very interesting. And the traffic steering, of course, is also very interesting to make sure that it's actually working. And especially if we get onto application layers, implementations have always had issues to differentiate applications that are not obvious. So if you have an obvious HTTP service, of course, any application will differentiate it correctly. But if it's Skype, for example, or if it's Viber or some chat protocol, those change their protocols over time, and Viber even does that on a daily basis just to circumvent censoring in some countries. So it's not that trivial to do application-based traffic steering. And even if you want to steer on Oracle or Citrix, I would think it's important to make sure that it actually works. So that was a quick summary of our test bundle, and now finally let's get to a case study, and I wished I could have shared with you the name of the vendor and the detailed results. I can't. I have the promise from the vendor that they want to continue and retest, but we'll see how it goes. Certainly you will hear from us with tangible named results in light reading before the end of the year. There is a queue of vendors who want to run public SD-WAN tests independently. So how do we test application-based traffic steering? So we would set up one of these typical hybrid WAN use cases that I've shared with you before. So let's say we have two CPEs in this case that are talking to each other. In this case, it would be a full mesh scenario, but we just declare, we declare one of the CPEs being the hub and the other one being the edge. They are connected over the internet, an emulated internet, obviously, and over an MPLS network or another network. They have connections to the SD-WAN controller mutually, and they have 2 or 3 different traffic types. So these blue, yellow, and reddish dashed arrowed lines are the different traffic types. And now we want to configure, and we want to see if the solution does that correctly. We want to configure traffic steering based on the application layer. So we need to emulate traffic that has different applications. We are sending it from both directions into these CPEs, and then we monitor what happens on the network side. So there will be 2 or more links between remote locations, and the edges should be configured here to prioritize the non-critical traffic A across the internet, and B and C should be across the MPLS link because they're critical or delay sensitive or something like that. Now, how do we actually change the internet quality? There are impairment emulators available commercially and open source that can actually artificially increase the latency, they can increase the packet loss and delay variation. So it's possible to emulate internet quality even in the lab. And it's important that it's possible to emulate this in a reproducible fashion. Because if we would just use the real internet, yes, that would be more realistic, but maybe we would have to wait for weeks or months until a real problem occurs in that specific ISP. So it's important to emulate that in the lab. So now you see a number of blackened logos here. And we have actually run this test here in the master and backup scenario with VRRP. So basically, these 2 CPEs here are connected with VRRP to determine, to detect which one of them is active and running. And we have run the SD-WAN links in an active-active scenario, like I explained before. So we wanted to make sure both of them are used. One traffic class, UDP traffic in this case, is steered towards internet, and FTP, like TCP-based traffic, is steered towards the MPLS. So in this case, lesson number 1, this is not real application layer, this is transport or session layer. So the vendor was actually able to differentiate the traffic based on, not on the application, but based on the session layer. Footnote, actually, if you want to say, my Citrix traffic is high priority, of course you could detect that on the application layer. You could look deep into the packets and try to find the Citrix protocols. What were they called? ICs? I forgot. But you could also just say, like, I know the IP address range of my data center. So anything that goes to my data center where the Citrix servers are will very probably be Citrix services. So I don't even need deep packet inspection. I can just say, like, this IP address range is high priority service just because this is my data center. So we ran this here, and then we checked a couple of things. First, we disabled one of the CPEs, the VRRP master. We measured the failure and recovery times, and then we switched it back on, and we switched off the other one. So that's actually quite important, because in many cases we noticed that a failover event, the first one, is the standard test case with vendors, it seems. Not many actually seem to test the recovery and the failover from the other side. It's important to see if when the service recovers, if the active-active scenario is actually getting back on track, or if all of the traffic that failed over stays on that one side, which would be unfortunate, because there will always be some failure. So after a couple of months of operation, if you have purchased a solution that doesn't rebalance traffic after units come back into operation, after a couple of months you would see only one of these links used by most of the CPEs. So we checked if the master can recover. So after it recovers, the traffic was actually forwarded through both links again, appropriately for the UDP towards the internet, FTP towards the MPLS. And then we failed the backup VRP, and we measured if the traffic was forwarded, if all services were forwarded over the other line. Now, the interesting part here is this is an end-to-end service. So it doesn't help only if the VRP master and backup are talking with each other. So, of course, in VRP, here on the local side, the other side will take the virtual IP address. So for the LAN access, for the local area network, the failover will be really fast. But the remote side needs to be informed as well, because this one tunnel isn't working anymore. This tunnel is supposed to get all the traffic. So the other side needs to be told that it needs to send traffic towards the other side. As long as it hasn't detected this, it hasn't been informed, it hasn't taken action, all of the traffic is sent into nirvana. It doesn't arrive anymore. So that's actually what takes a lot of the challenge here, and that's why I said to expect multiple seconds of failover time. And that's not a new challenge. That's a challenge we've had in all transport networks. It's the same old routing stuff. So basically, if we use BGP here, and OSPF like we used in this case, OSPF for direct adjacencies, BGP for exchanging routes, customer routes, then first OSPF needs to notice, oh, my peer has gone. And then BGP needs to notice, well, that route doesn't work anymore over that next hop. I need to reset it to the other direction, to the other tunnel. So that can take quite a while. And we're going to retest this now in the lab with BFD switched on. So the only way to really substantially reduce the failover times is to have a continuous data plane monitoring protocol. It's called bidirectional forwarding detection, BFD. And that will actually notice very quickly if the tunnel is not working anymore. Unfortunately, it also exchanges packets all the time that are not usable data load anymore. So we tested this, and we noticed it all worked great. It just wasn't failing over as fast as the vendor had expected it to be, and so we need to rerun the test. So the next point was like, what happens if the link fails? So in the previous case, we failed the CPE. Now we fail the link. Let's say the internet stops working. Again, we measured the failure and recovery time, and we expected all of the traffic to fail over to the other side. Like in this case, the low priority traffic to fail over to the MPLS side. And in the same case, IBGP was used to propagate the site prefixes, and that contributed to the time required to recover. So I had some additional, more complex cases, which I actually wanted to show in a video that I had prepared, but again, I can't show this video, unfortunately. So we played around with this failure, and as I said earlier this morning, the internet rarely fails completely. It fails because it has too much of a packet loss, it's congested, has too much latency, and so on. So we actually played around with a number of criteria. We increased the packet loss to like 3%, 5%, and we created pretty complex application steering policies that said this type of traffic should be failed over to the MPLS side if the packet loss reaches 3%, and all traffic should be failed over if the packet loss reaches 10%. Because obviously, you know, if you have voice over IP, for example, running, 3% packet loss is already a lot. I'm not sure how many codecs can actually survive 3% packet loss, but you should make sure that there is a low packet loss on voice over IP services. But if you have, let's say, a web browsing session, temporary packet loss is not so much of a deal. You know, yes, it delays the session, but it'll come back. So we validated those steering policies, and we played around with, you know, switching stuff back and forth, and that was actually pretty nice to see how it worked. So conclusion of this tutorial. SD-WAN is a great overlay VPN solution. I hope I didn't come across too negatively. I mean, that's kind of the role of the tester. You see the reality, and it's important not to become too negative. I think it's a really cool solution in terms of we have waited for this. It combines a number of things, solution aspects in a way that have not been combined before in other technologies. At first glance, it looks easy, like overlay 2 boxes, deploy them, done, wonderful. You get so much more bandwidth, so much more reliability, resilience at low cost using internet. In real life, things are more complex, as always, so that's the case, but that's why we're here, and why we're educating ourselves, and why EANTC is testing these solutions to make sure that even the more complex things work smoothly. Still, at this time in the technology lifecycle, we do recommend to compare solutions that you consider purchasing before taking a deployment decision. There will probably be limitations, but I think for many cases it's normal. In our technology, in our times, there are always limitations. The technology cycle is fast and nothing is perfect. That's fine. It's just important to understand what are the limitations. Are those limitations that I can accept? And we would suggest to focus on a number of areas, not only test one area, not only get into a vendor lab and so just show me how it works and they have a nice show with 2 endpoints. That's useless from my point of view. It should really be tested based on the specific individual requirements that exist for your network. And take all of those into account, and I think we will all be happy people with SD-WAN. So that's all from me today. Thanks very much. Thank you. So are there any questions? Oh, please.
Hey, Carsten, this is Rajesh. Fantastic presentation. This was really good. Question, you said between the controller and the endpoints of UCPEs is most of it, right? So wouldn't it be very difficult to recreate, for any service provider, to recreate thousands and thousands of CPEs in the lab to test for scalability? I mean, short of redoing the entire network, I mean, how can they feel confident about the scalability?
Right. Yes, it is difficult to recreate a scalability scenario in the lab with many CPEs. That said, my experience so far is vendors have often done that because they need to do it for their development anyway. If a vendor has no clue how to run a test scenario with thousands of CPEs, they have no experience in this, and they should make no claim on how their service will work with thousands of CPEs. It's definitely not a good idea to test this in service. So the vendors that we've worked with so far have an understanding, and as I'm not sure if I mentioned, so maybe there is a virtualized environment and you can test with that. I've also tested with some hundreds of CPEs in physical, but it's a lot of work, as you know, in cabling and everything. Any more questions? Over there?
Yeah. Are you testing applications as well in your performance groups? So you're testing if you can hear me. I mean, I see you doing all the fragmentation tests and packet drop and stuff. Are you actually testing sort of typical applications that are being used?
Yes and no. So we do test applications. Typically, for an SD-WAN scenario, we would just emulate this, and we would abstract from the applications as far as we can. If there is some unified threat management or intrusion detection, of course, we need to test at the application level, sometimes even with real applications as a foreground load, not even emulated ones, because it's too complex to emulate them. In most cases, we can just abstract from it, and as in this case, I just presented tests with UDP and TCP traffic, because that's the level at which the solution differentiates anyway. But yes, of course, we test with real applications.
Okay, thank you.
One challenge is on the multi-vendor support. As of today, different SD-WAN provider box cannot talk between each other. From a service provider perspective, we want to avoid vendor lock-in. How to mitigate this challenge?
I think we can compare this a little bit with what what we've seen in the SDN-WAN technology area in the recent past. So SDN, not SD-WAN, but SDN has been around for a number of years. In the beginning, we started testing interoperability between switches and controllers, and that we still do that, but in most cases, actually, vendors now say, well, our switches and our controllers are one bundled solution, but it's possible to test interoperability between multi-vendor scenarios, between controllers and orchestrators. So I guess that is probably going to be the case for SD-WAN as well. So as I said, the MEF effort, the broadband forum effort, and other efforts are towards standardizing these northbound interfaces, and that's where we will probably see multi-vendor solutions. It's a little bit like in other access technologies where service providers have deployed like certain geographical areas, or in mobile networks, for example, let's say north of Germany is one EPC vendor and one antenna vendor, and south of Germany is the other one, and nobody expects everybody to play with each other, but there is multi-vendor support on the northbound and management side. So,
yeah,
okay,
Carsten, one more.
Yeah.
Yeah, hi. So I saw in your presentation you said that OSS BSS integration was the biggest hurdle. You also mentioned that as of now, you're not aware of anybody who's implementing the MEF standards.
Mm-hmm.
Are you aware of any work going on that is addressing that number one hurdle, or is that anything that you are looking at?
Oh, I think a lot of people are working on this, but you know, as a humble test lab, I don't claim to have a complete overview of the whole market. So I will be sitting down here for the rest of the week and listening carefully to what other presenters will have to say. So I'm sure everybody's working on it. I'm not sure like how much of it has matured. So one last question in the center, and then I think we'll wrap up.
Oh yeah, the question is regarding broadband access.
Mm-hmm.
I have a question regarding broadband access. For example, many providers use digital subscriber line access or GPON, and for this they use PPP over Ethernet, where restriction is to have the 1492 MTU. Will this put a restriction to SD-WAN because you may have a lot of fragmentation regarding IPsec and so on?
Well, I think any transport technology has specific MTUs, and I guess in general, SD-WAN will reduce the maximum packet size, differently for different access technologies. And yes, PPPoE is a little harsh, but whether it's 1492 or 1500, I think is not so much of a big difference from my point of view, because SD-WAN will eat away more bytes anyway. So anybody who assumes that their contribution loads can have the full 1500 bytes is going to suffer anyway. So people will have to accept lower MTU sizes in the local area network of like 1300, 1400 bytes. But again, I'm going to listen to the vendor solution presentations this week and see what solutions vendors are coming up with. Okay, so thanks so much for listening to this tutorial. I'm really very happy about this audience. Thank you so much. I hope you'll have a great conference in the coming days, and have a good lunchtime. Thank you.